Hello and welcome to the Week 10 Math 2419 weekly review. This session will be covering iterated integrals, double integrals in volume, and lastly we'll start talking about some change of variables to polar, but we'll just touch on that briefly. Let's go ahead and get started with some iterated integrals. And if you recall, last week we were talking about taking the derivative with respect to multiple things. So in this lecture, or in this review, we'll be going over with respect to multiple variables. So let's say you have a function of x and y, so something like f of x comma y. And if you have this function, well, you can actually take the integral in two different ways. You can take the integral with respect to x, we denote that by writing dx, or you can take the integral with respect to y. And if you recall, this is similar to how when you have a function of multiple variables, you can either take the derivative with respect to x or the derivative with respect to y. Same with integration. You can either take the integral with respect to x or the integral with respect to y. And also similarly to differentiation, whenever you take the integral with respect to x, you would treat y as a constant. And whenever you take the integral with respect to y, you treat x as a constant. So as a quick example, let's say you wanted to take the integral of 2x y plus y squared with respect to x. And we know we're integrating with respect to x because this here is a dx rather than a dy. So the integral of 2xy, since y is a constant, is equal to y times the integral of 2x plus y squared times the integral of just 1 dx. And all I did is I split apart my two separate parts, 2xy and y squared, and then I pulled out all of my constants. In this case, because we're integrating with respect to x, our y terms are constants, so we can write it like this. And then, of course, it's just a simple integral with respect to x. Of course, we also have to have our plus c. But in this case, our plus c has to be a bit different. We actually say that c is a function of y, because in this case, y is a constant. So our constant term can actually have any number of terms with a y in it. So for example, if we had c of y equal to y cubed plus e to the y plus 1, well then our integral in total would be yx squared plus y squared x plus y cubed plus e to the y plus 1. And if we took the derivative with respect to x of this, well, we have first 2xy plus y squared, then y cubed, e to the y, and 1 are all treated as constants, so they all go to 0. And we see that if we integrated with respect to x and then took the derivative with respect to x, we would end up with the exact same thing we started with, which is 2xy plus y squared. That all checks out. And similarly, if we wanted to integrate with respect to y, then we would get a constant term that's the function of x. All right, so we can also take the integral multiple times in a row. But again, this really isn't super hard. Let's say we had a double integral like this. Notice that we have exactly two integration symbols, one right here, one right here, and these correspond precisely to two different differential terms, basically. We've got a dx here and a dy here. And the easiest way to think about this is to say, I basically just have two separate integrals. This first one I can evaluate completely as just a single integral. So we can say, what is the integral from 1 to 2 of 4xy dx? Well, that's pretty easy. We can move the y out front as a constant. Y integral from 1 to 2 of 4x dx is equal to y times 2x squared from 1 to 2. And that, of course, gives us 2 times 4 minus 2 times 1 gives us 3. Oh dear, I did that math so wrong. 2 times 4 gives us 8, minus 2 times 1 gives us 6, so 6y there. All right. Next up, we can take this answer and basically plug it in because this was the solution of this inner integral. So we would basically just pull this out and swap it out for this portion here. And then our second integral becomes the integral from 0 to 4 of what's just 6y dy. And again, this is a simple integral. That's 3y squared from 0 to 4, which gives us 3 times 16 is 48 minus 0. Perfect, perfect. So we can really essentially treat these double integrals as just doing one integral and then doing a second integral. It's still a straightforward process, even though it's a bit more work than just doing a single. Okay. Okay, let's go ahead and do another example. This one, though, is going to be a bit different. Let's say we had the integral from 0 to 2, and then we had the integral from 0 to x squared of this function 4x plus 2y dy dx. One important thing to note is here we're integrating with respect to y first. And what that means is we have to treat x like a constant. So because x is treated like a constant, we can actually use x as a limit of integration. We always want to have what's essentially a constant limit of integration. It can look like there's variables up here, but because we're integrating with respect to y first, it would be a constant in this case. If we had like instead of a dy in this green shaded portion, if we had a dx, that would actually not be allowed. You would have to rewrite it a bit to be mathematically proper, and then it would look, your answer would just look a bit different. And I don't think you should ever see that in this course, but that's a sign that you probably did something wrong. If you have a limit on the inside that is a variable that matches whatever variable you're integrating with respect to, that is a sign you did something wrong. And also, if you do have a variable as one of your limits, it should always be this inner limit. Outer limits should be constants all the ways. That's just one thing to note. All right, so let's go ahead and solve this integral. We basically solve it in the same straightforward process we did on the previous one. We first look at our inner integral, the integral from 0 to x squared of 4x plus 2y dy. Since we're integrating with respect to y, we can treat x as a constant. So that would be the integral of this inner portion. Our limits of integration are from 0 up to x squared. Wherever we see a y, since remember these are limits for y, we would plug in first an x squared and then a 0. And this, of course, evaluates to 4x cubed plus x to the 4th. And now we can take this portion and just plug it right back in to our integral right up here. That is a terrible looking arrow. I'll just draw another one really quick. That's slightly better. Okay, that leaves us with the integral from 0 to 2 of now 4x cubed plus x to the 4th dx. And this is, again, just a straightforward integral, x to the 4th plus 1/5 x to the 5th from 0 to 2. And that gives us 16 plus 32 over 5, which I believe is 112 fifths as a final answer. All right, here we go. One quick practice problem. Go ahead and evaluate the following double integral. Just the integral from 0 to 4, y to 0, e to the y, dx, dy. I'll give you a minute or two to work on that. All right, let's go over this problem. So first off, we just solve our inner integral, which is fairly easy. Since we're integrating with respect to x, we treat e to the y as a constant, and we get x e to the y from y up to 0. And that is, of course, 0 minus y e to the y. And we take this minus y e to the y, plug it into our outer integral. Now, this integral does actually require integration by parts. We can let u be equal to, first off, I'm actually just going to move my negative sign out front like that. Since it is a constant, we can let u equal to y, dv equal to e to the y, and we get 1 e to the y, and then e to the y, 0. I'm using the shortcut method, plus minus. So this integral evaluates out to y times e to the y minus an e to the y, and then from 0 to 4. Perfect. We can plug in our limits, and we get minus 4e to the 4th minus e to the 4th, then minus 0 minus e to the 0th. E to the 0th is 1, so that becomes plus a positive 1, and that gives us, if we distribute our negative, we would have 1 e to the 4th minus 4 e to the 4th, gives us negative 3 e to the 4th minus 1. All right, now let's talk about something that's pretty important, and that is switching the order of integration. Okay, let's say you had this some integral. Let's say it looks like 0 to 4 integral 1 to 2, and we'll just make a really simple function, xy y dx. Well, by the way this is set up, it tells you basically have to integrate with respect to y first, since that's your inside variable. But you can actually switch it if you want to integrate with respect to x first. And when all of your limits are constants and there's no variables in them, it's super easy. You can just swap the limits. Integral from 1 to 2, 0 to 4. Your function actually stays the same. Now you're integrating with respect to x first. Notice that we actually kept the same variables that were, or the limits that were attached to a specific variable remained the same. For example, this 1 to 2 was attached to this y, and on the second integral, that is the same. On the first one, it was the inner. On the second one, it's the new outer. So switching the order of integration is really easy if all of your limits are constants. If your variables and if your limits of integration are instead variables, then it does get a bit weird. So let's say the limit from 0 to 1, and then the limit from y up to 1 of some function e to the x squared dx dy. Well, here we can't integrate e to the x squared. It just is impossible to integrate using normal functions. So clearly we can't integrate with respect to x first. So we might want to consider swapping the order of integration. But if we just go ahead and try and swap the order of integration, then suddenly we have this y, which is a variable, as an outside limit, and that is not allowed. Not allowed. So clearly we need to do something a bit different. Maybe if we could write our region of integration in terms of x variable instead, that we could then put as an inner limit. So I'll draw an illustration to maybe clear things up. Let's say we wanted to sketch the region of integration. Well, we clearly can see that our y value is going to range from 0 up to 1, since that is our y value. And we also know that our x value is at most 1, and we can see that from this 1 right here, since that's associated with our x. And also, our x value always has to be bigger than our y value. So we'll go ahead and put a 0 here, a 1 here. X is always smaller than 1. And because this is a limit for x, this bottom limit y, we can actually read it as x is equal to y. Not 1, x is equal to y. There we go. And if we drew the line x equals y on our graph, well, it would just be this line like so. And it would hit at 1, 1, which is about right there. I'm a bit off, but that's not bad. And what we actually know is that our x value starts at our lower limit on our y value and goes up to 1 like so. So we can kind of see that our region of integration would then be this lower triangle underneath the line y is equal to x, where x is bigger than, or x is smaller than 1. Now, if we wanted to write the same region with a constant x value, or sorry, with a constant x value, we would need to write it in terms of y instead. I'm going to draw instead, because it's a y, a vertical, what's called a representative rectangle. And we can clearly see that the constant x limits be this 0 here and this 1 here. Since that is the lowest our x can be, lowest x, and this is our biggest x. Now, if we wanted to put our y values in terms of x, clearly our lowest y is going to be this constant line here. Our upper y for any given x value, though, is actually going to be along this line y is equal to x. And that gives us our upper limit for y. Tells us that our upper limit should be equal to exactly x. So we can rewrite integral as the integral from 0 to 1, which are our new x limits, and the integral from our lowest y, 0, to our biggest y for a given x value. And that biggest y for a given x value would simply be x. Our inside function stays the same, but then we swapped the order of integration. So now it's in terms of y rather than x first. Now we can actually perform this first integral because we treat everything with an x in it as constant. So it becomes the integral from 0 to 1, y e to the x squared from 0 to x. When we plug in x, we get the integral from 0 to 1 of x e to the x squared dx. And this can actually be solved by u substitution if we let u equal to x squared. And we would see that du is 2x. We actually have a 1/2 du. I'll actually just write this out a bit. So then 1/2 du is equal to x dx. So we end up with the integral from, if we wanted to plug in our limits of integration, u is equal to x squared. So 0 would correspond to a lower limit of 0 squared. 1 would correspond to an upper limit of 1 squared, which is still 1. And here we just have du e to the u, which is, of course, e to the u from 0 to 1. Since I put my limits in terms of u, I can actually just plug that in, and we get e minus 1. Oh, I forgot my 1/2 right there. I forgot that. So I'll just put that out as a constant. And I'll just put it out front as a constant there too. Regardless, the answer is 1/2 times e minus 1. And that is sketching the order of swapping the order of integration. Some tips. Always, always, always draw a picture to sketch your region of integration. If you don't, things tend to get confusing, or I guess more confusing, but this is not that. Thank you for pointing that out. Let me go ahead and share my screen again. I don't know why it stopped. Can you see it now? Cool. All right, I'm actually not sure how, let's see, give me one. All right, I think my connection must have skipped and it made me stop sharing my screen. Okay, all right, I think we're good. I'll just really quickly run through this problem one more time since I'm not sure how long I was disconnected for, but basically we wanted to swap the region of the order of integration. We couldn't swap it just by switching the two integrals because that would give us a variable as an outside limit, which is not allowed. So what we did is we sketched our region of integration, and we found that it looked like this triangle underneath the line y is equal to x. And we also discovered that our x value had to range from this point, y is equal to x, up to a biggest x value of 1. And we got that from our original limits on x. Then we put that same region in terms of y, right here and right here, and we found that our y values had to go from a constant low of y is equal to 0 along this x-axis up to a point on this line y is equal to x, which gave us a biggest value of y, that was equal to x. And that allowed us to rewrite our order of integration as being the integral from 0 to 1, then the integral from 0 up to x of our original function dy dx, so with the y first. And when we evaluated it all, we ended up with 1/2 times e minus 1. Any questions? All right, in that case, we'll do, I think, one more example with swapping the region of integration, swapping the order of integration, before doing some practice problems. And in this case, we're not actually going to bother evaluating the integral. We're just going to swap the order of integration because that's basically the new concept here. Let's say we have integral from 0 to 1, the integral from x squared up to x with respect to y first, of course, because our inner limits are in terms of x, which tells us we have to integrate with respect to y first. First off, we're always going to want to sketch the region. Always, always, always. We can see that our x values are ranging from 0 up to 1. So we can kind of go ahead and put that down. Our x-axis, 0 up to 1. And our y values are actually ranging from these points, y is equal to x squared, up to the line y is equal to x. So if I sketch those, let's see, we'll try to draw this a bit neater, but I don't know how neat it's going to get. If we drew the line y is equal to x squared, that's going to be a parabola, looks something like this. Kind of looks awful, but that's okay. And we'll want to label that, of course, y is equal to x squared. And here we would have the line y is equal to x, like so. And of course, we want to label that as well. And for convenience sake, I'll move this. Just move the Y over. Okay. And this would, of course, be the point 1, 1, which is where these two lines intersect. Well, we can see that our y value ranges from a point on this line y is equal to x squared up to a point on this line y is equal to x. So our region is this area in between these two graphs right here. Now, if instead of having our x terms constant, we wanted to have our y terms constant, we simply look for the smallest y and the largest y. And the smallest y, of course, occurs right here, which is y is equal to 0. And the biggest y occurs all the way up here at y is equal to 1. So that tells us that our new y limits are going to be from 0 up to 1. Now, for our x limits, we actually need to put those in terms of our y values. And we can draw a horizontal representative rectangle for what's essentially a single constant y. And for any given value of y, we'll say right there, we can see that our x value, our smaller x value is right there. I'll mark that down here actually, so I have something to write. A smaller x value corresponds to the line x is equal to exactly y. Our larger y value, our larger x value is on the line y is equal to x squared. But since we want to write that as an x equals, we would have to take the square root of both sides, and we get x is equal to the square root of y. And that tells us that y is less than or equal to x is less than or equal to square root of y. So then we could rewrite our limits. Remember, our constant limits go first. Then we have our inner limit, y up to square root y. Now we have our dx first, and then our dy. And that would be our function with switched order of integration. Any questions? All right. In that case, I'll go ahead and give you a couple of practice problems. There are going to be a couple more practice problems on this than on most of the other topics because I think this is probably the most important thing we're covering today. So for practice, just sketch the region and then swap the order of integration. Don't actually evaluate the integral. Because there is no point. Let's see, the first one, go from 1 to 2, from 1 up to y of dx dy. And then for the second one, I'll actually put it way over here. Integral from 0 to 1, integral from x up to the square root of x y dx. And I will give you a couple of minutes to work on that. see. Is it 1 is less than x than 2 is less than 2, and x is less than y is less than 2 for the first one? Yes, that is correct. And just for the sake of everyone who is watching the recording, I'll just go ahead and draw a sketch of the first region. Just realized I was muted. Sorry about that. Um, For the second one, you said that 0 is less than y is less than 1, which is correct. The other limits, though, y is less than x is less than y squared, is actually a bit tricky. Let's think about where y is between 0 and 1. Which is actually bigger? Is y bigger than y squared, or is y squared bigger than just plain y? Or y values between 0 and 1? That's a good thought, but let's just pick any one y value. Let's say 1/2. If we take 1/2 squared, that's 1/4. Oops. 1/4, which is actually smaller than 1/2. So if this is the y squared term, we could say it's actually smaller than our original y term. So we can actually make a sketch of this. Let's see. Here we go. If we wanted to sketch our region of integration, we could see x values are from 0 up to 1. Can't draw anything today. 0 up to about 1. And then our y values range from this line y is equal to x up to this line y is equal to x squared, like that. And that's close enough to the point that we'll call it good. And this intersection point is, of course, going to just be 1, 1. So that goes there. We'll go ahead and take that out so we can do a bit more highlighting. And then that would be 0 right there. Okay. We know that our x value starts, or sorry, our y value starts at this line y is equal to x and goes up to this line y is equal to the square root of x. If we put these two lines in terms of x, so an x equals equation, that would give us that x is equal to y squared, and of course just x is equal to y. But then we can kind of sketch out what our region looks like. It's this whole area right here. And if we wanted a horizontal representative rectangle, it would also be in the same region. Now, because our our outer limits were at first x, so now they'll be y, so we just pick our minimum y value and our maximum y value to be our new y limits. So clearly y is between 0 and 1. Then for our x limits, we actually have to look at this representative rectangle. We can see that for a single given y value, we'll say right there, we can see that our smallest x value actually lies on this line, x is equal to y squared. And our largest x value for that single given y lies exactly on this line, x is equal to y. And that tells us that y squared is less than x, which is in turn less than y. So we could rewrite this order of integration like so. Yeah, you do have to look at it horizontally. That's why I'm a pretty big fan of using these representative rectangles, because you can actually kind of trace out what's going on. You can say my smallest x value, do it again in blue, my smallest x value is right here, and it's on x is equal to y squared, and then it goes all the way up until I hit my biggest x value on the line, x is equal to y. You can also think of it in terms of like for a constant y. So just like picking one constant y value, because when you do your first integral, I guess I should have finished writing out this statement. Because it's with respect to x, you can basically treat y as constant. So if you look at a single constant y, you can look at the lowest point on that constant y and the highest point on that constant y. And it can be pretty helpful sometimes. And I'll just finish off by highlighting to be consistent, like so. Okay, and that would also be highlighted, and that would be highlighted. Cool. Okay, any questions with this problem? Yes, you always have to have your variables on your inside integral. You should not have them on your outside integral because that causes problems, because rather than getting like an actual number as your answer, you would get a function as your answer. Um, so I guess maybe we can kind of illustrate that with the previous example. Let's see. So if we had, like in this case, we had a variable on the inside. If we had a variable on the outside, we say it's not really allowed. I guess technically you could do the integral, but then once you did your second integral, you would have some thing, and then you would basically plug in 1 and also plug in y, and that would get you something with a y in it. So basically a function of y, but we could actually find an actual number for it, which we did down here. Oh, still using highlighter. But yeah, we could find an actual number that we did down there, so it's just better to find the actual number when you can. And I don't think in this class you'll ever really see variables on your outside limits, so a good rule of thumb is just keep your variables on your inside limits. That answer your question? All right, did you have any other questions with it or the first problem? When we looked at it horizontally and the signs are switched, is it technically negative? I'm not quite sure what you mean by the signs are switched. Could you elaborate a bit? All right, all good then. Okay. Um, yeah. Anyway, I think that's probably enough for swapping the order of integration for now. Since we are a bit short on time, I think I would like to discuss a bit of what the meaning of a double integral is. Of course, we're not going to get too into it since this is just like a review session, but it's always good to have a reminder. So if you recall back when you learned about a single integral, um, One of the key things of a single integral is it actually gives you an area under a curve. And the thing about double integrals is they kind of do the same thing, but 1 degree up, if that makes sense. Rather than giving area, which is like 2-dimensional, it will give you volume, which is can be thought of as 3-dimensional. Volume under like a surface. So in 3 dimensions, you would have a graph. Let's see if I can draw this out. And it would almost look like some kind of sheet or plane or something. Well, the area of the double integral would give you like the volume under in the shape on a specified region in the plane. So it would give you kind of like the area of this weird looking, almost like a box. So something like that. And that is what a double integral does. So, for example, let's say I wanted to find the volume of the region under this simple plane x plus y plus z equals to 1 in the first octant. All right, let's try and draw a picture. First off, though, I'm going to go ahead and rewrite my plane to be in terms of z. So z is equal to 1 minus x minus y. And I basically can reason through what this plane looks like. And it's basically going to form a little tetrahedron in my first octant. So let's say this is my x-axis, this is my y-axis, this is my z-axis. I would have a plane cutting through and making a little tetrahedron. Of course, it would extend out like this. And it's, of course, going to be like a huge plane and stuff, but we're not actually going to concern ourselves too much with that. Basically, we're only concerned with the volume of this little tetrahedron right there. And if we look at this lower portion, the part of the xy plane that it covers, you could actually sketch that out. We will. It's going to be a bit odd since you're going to have to think about like kind of spinning it since this is our x-axis and this is our y-axis. But end up with a region made by this little triangle. So it looks like this. And that would be our region of integration in this problem. Now we can basically choose which variable you want to integrate with respect to first. I'm just going to arbitrarily choose to integrate with respect to x first, because then my x limits are going to be in terms of y, and I just like working with y equals functions a bit more. So since I'm integrating with respect to y first, or sorry, with respect to x first, then that means that my y limits should be constant. So y goes from 0 up to y is equal to 1. Easy enough. Now, for an x limit, I would have to say my x value for a constant y value, we'll say right there, my x value starts at this 0 line, and it goes up until it hits a point on this line. And this line I actually know is the line y is equal to 1 minus x. And I can explain that a bit more in a second. But what we're actually integrating is simply going to be our original function that we rewrote. So that would be 1 minus x minus y. And then dy dx. Okay, okay. Cool, cool. All right. Cool. I think I maybe misstated a couple of things. Um, because I tried to put my function, sorry, because I put this line in terms of y equals, that means we're actually integrating with respect to y first. But regardless, you can still see our x value ranges from 0 up to 1. And I found this line, y is equal to 1 minus x, right there, by taking a look at this plane. Since I know it's a plane, then I know it has to be straight. So that gives me a only linear functions. That could be a possibility for that. And I also knew the intersection points right here and here, because I know that x plus y plus z has to equal 1. So if x is equal to 1, well then clearly y has to equal to 0. And if y is equal to 1, then clearly x has to equal 0. So that's how I found my intersection points. And that gave me 2 points right there and right there. And since I knew it was a line, that was enough to write this function of a line. And now we have set up our integral, and we can basically just evaluate it. First off, of course, we solve our inner integral. That gives us, with integrating with respect to y, we would get 1. The integral of 1 is y minus yx minus 1/2 y squared from 0 up to 1 minus x dx. If we simplify that, we get the integral from 0 to 1 of 1 minus x minus y times 1 minus x minus 1/2 times 1 minus x squared. Oops. Sorry, there should not be a y in there. That should be a 1 minus x times x. There we go. All of our 0 terms would cancel out, so I'm not too worried about those. If we continue to simplify, we can combine all of our like terms. You can double check me on this, but it comes out to be 1/2 minus y plus 1/2 y squared dy, sorry, dx. Nope, I am confusing myself. That should be a dx. Cool, cool. All right, yes. Okay, and from here, this is just an integral of a standard one-dimensional integral that you've been doing for quite some time now. So we can go ahead and figure that out. 1/2 y minus 1/2 y squared plus 1/6 y cubed from 0 to 1. And that gives us 1/2 minus 1/2 plus 1/6, which gives us 1/6. Cool. Any questions? How did I get that 1/2 minus y integral? Oh, you are completely correct. All of these should actually be x's, sorry. I was kind of working off of notes, but I did the problem previously. Let me just, what I did is I miscopied down my notes. That's what happened. Thank you for pointing that out. Basically, I was just simplifying this whole term, except wherever there were x's, I wrote them as y's. Yeah. So that should actually say 1/2 x minus x plus 1/2 x squared dx. Okay, there we go. Yeah, that's how it should look. And cool. And of course, then we can actually integrate that 1/2 x minus 1/2 x squared plus 1/6 x cubed. 0 to 1. It does in fact give us the correct answer, 1/2 minus 1/2 plus 1/6. Minus 0, of course, gives us just 1/6 as our answer. Answer is still 1/6, but now we actually wrote down the correct things, so thank you for pointing that out. Quick question. Have you talked about change of variables to polar in class yet? With double integrals specifically? Yeah, I get that. I think we'll probably just touch on it next week then. That way I can do one practice problem with volume. Um, let's see. The practice problem is going to be just find the volume under the surface z is equal to 6 minus 2x on the region yeah, just on a bounded by 0 is less than or equal to x is less than or equal to 2, and 0 is less than or equal to y is less than or equal to 3. And really, the hardest part of this problem is just setting up your integral. It's just a fairly straightforward word problem, though. But the key thing is just recognizing the fact that volume means double integral. I'll give you a minute or two to work this out. Um, how would you set up the integral using y? It is, so basically, you could think of it as a line on the xz plane, but then if you expand that line with a constant y value, then it would basically become a plane in 3D space. So that's an interesting thought, but let's see, maybe we can sketch this out. Um, here's our y, here's our z, here's our x. The line z is equal to 6 minus something along there. And then it would go down to about right there where x is equal to 3. But you could actually stretch this out with a constant y value, because that condition would still hold, that 6 minus 2z would be equal to x, and it actually just forms a big old plane like that. Yeah. Good question, though. Is x until 2 or 3? That says 2. Sorry about my bad handwriting. That is a 2. This is a 3. This was just kind of to illustrate the plane itself. Technically, this would be a 3 right there, but it doesn't actually have any impact on this problem here. It is like a kind of weirdish trapezoid shape. Saying that it's a trapezoid specifically is maybe a bit misleading, but it would be like this kind of weird looking trapezoidal prism. Here. My drawing skills are getting worse and worse. Where you've got something that looks like this. I should just drop that down, and then here you have like a, yeah, so it would kind of be trapezoidish looking thing like that. Trapezoidal prism, I think, is what it would technically be called. That point there would be 2. You got 24. 24 is correct. And really quick, we'll just go over this. The setup would be, we can take, since it's a square region, we can actually tell that, yeah, we can actually tell that, since we have a square region, let me start this sentence over. Yeah, I cannot talk. Because we have a square region, neither of our limits of integration should need to be variables. So we can actually just set it up pretty plainly, 0 to 2. 0 to 3, since our y limits are the inner limits, we'll be integrating with respect to y first. And I just put my function in terms of z as the function that I'm actually integrating. And that would be 6y minus 2xy from 0 to 3, which gives the integral from 0 to 2 of 18 minus 6x. The x terms would all cancel, so I'm not concerned about those. Dx equals to 18x minus 3x squared, not 6, from 0 to 2, and that gives 36 minus 3 times 4 is 12, gives 24 as our answer. So, yep, nice work. All right, that is all I've got for today. I don't want to start change of variables to polar since that'll take a bit. So we'll just cover that next week. But do you have any questions about anything we covered today? Or even just anything in the class? All right, cool. Well, thanks for coming and have a nice week.